Can't figure it out, so I might be a little bit boomy, but that's okay. So, today we're doing a review, trying to get you all ready for the midterm. I have a good moment. I passed my motorcycle test this morning, and that had all kinds of gotchas, which hopefully we don't have on this test. We just have security proofs. And what I heard back in the survey was that security proofs are sort of the most interesting thing, and that's confirmed what Professor David and I had in mind. So today we'll walk through a couple of proofs. We'll start with ElGamal, do a security reduction. And then I have the multi-ciphertext argument to walk through. Hopefully we get time for both. Apologies, we're starting a little bit late. You should already be familiar with these three elements. So this is the definition of CPA security. Remember, the CPA security game is played between an adversary and a challenger. So challenger sends a public key, and then the adversary sends back two messages. Are there any restrictions on what those messages can be? Or adversary can do whatever they want to. The idea is the adversary can do anything within a polynomial amount of time, including they could do their own encryptions on this side. And they could even try and do decryption or encryptions that don't follow this precisely. So they could go through and say, okay, I'm going to make an encryption, but I'm going to choose a fixed value of y. They can do whatever. Adversary can do whatever they want to, but the challenger is going to pick with a 50-50 chance, uniformly at random, one of these two messages, encrypt it, send it back, and the adversary has to tell you which one it was.
So just checking, there's no distinction between CPA and CPA2, right? In the sense there's no fixed timing when the adversary sends the two messages.
Yeah, so because with PKE, the adversary can do their own encryptions, right. There's no CPA2 right. As there is for symmetric key. Right. Yeah. So this is just the mechanics of how ElGamal works. We're going to set up a group. We're going to pick some exponents. And this kind of looks a lot like Diffie-Hellman, but done instead of two parties being online. We're setting it up in such a way that you can send a message and somebody can decrypt it offline kind of idea. And speaking of, this is the decision Diffie-Hellman assumption. The idea is that an adversary cannot really tell the difference between getting g to the x, g to the y, g to the xy, and g to the x, g to the y in some random element in this group G with anything other than negligible probability. I made a slight change to the textbook definition in some of these random choices just to eliminate some of the obvious weak points, but that's only really a practical consideration. The theoretical construction still holds with high probability. Questions about the setup before we go any further? All this makes sense? This is all stuff you covered? Great. So basically what I want to do is that we want to prove that ElGamal is CPA secure. That's what we're looking to do. And the way we're going to do that is I'm going to produce a security reduction. So somebody want to give me an idea of basically when I say I'm going to do a security reduction, I want to use this assumption and this game. What do I need to produce to do a security reduction here?
Construct another adversary that utilize adversary that breaks ElGamal to break DDH.
Yes, exactly. So I'm going to produce a new machine such that if you give me some adversary that can break this in this game, I can break this assumption. So I'm going to call that machine B. I like calling my secondary machines B. Some people call them A prime. And this is what machine B is going to do. And I'll show you more in a drawing. anything else. So actually what we have is challenger. This is our B, and this is our A. So remember, our A breaks this game. So our B has to simulate this game to A. So as in here, the challenger is going to send to B. Come on, any marker that works. Description of the group, some generator, some X, some Y, and some Z. And we don't know whether this Z is some arbitrarily random value in the group or it's G to the XY. Okay? So B has to simulate this game. So what's the first thing B has to do?
Keep the public key.
Yes. Any thoughts as to what makes sense as a public key? Considering what the public key definition is from here.
I want to ask why the X is sample from 2 to the...
That's what I was pointing out earlier. I made some choices in this definition to eliminate some practical problems. Normally this is 0. I don't remember if it's 0 or 1 in the textbook definition. What's the problem if this is 0 or 1?
I mean, 1 would be okay, but I don't know why 2 would...
Why would 1 be okay?
Because 1 is the same to sample just from ZP minus 1.
Okay, so what happens if I use 1 here?
Okay.
Yeah. Yeah, 0 and 1 are problematic for practical purposes. If G is large, which it has to be for security, like you want your lambda to be big enough and G has to be large, has to grow with lambda, then the probability of you picking 0 or 1 is very low, and therefore theoretically this holds. Practically, you would never ever want to choose the first.
Makes sense.
Yeah. Okay, so what's a good choice for PK given what the machine B has access to?
Just X.
Just X for the public key. So they're just going to send X. Look at the definition of the public key.
Oh, and the group description.
Okay, so we're going to include the group description and then just lowercase x?
No, I mean group description includes the generators, right?
Yeah, so we'll include the generator. And then just lowercase x?
Big X, I don't know.
Ah, capital X, yes. Which we know is G to the X. Okay, what was our next step here? Okay, so next our adversary A is going to pick 2 messages. Any thoughts as to what B could do at this point? What could B do to try and simulate this game?
We could have paired a coin of its own.
Yes. So B is going to flip a coin. That's R randomly. All right. And we want to simulate encrypting a message. So we're going to say the C star. We want to simulate some encryption. So here's our definition of our encryption here. What could we do that would simulate encrypting either M0 or M1?
just set GR, where is it gamma or R?
So this is Y,
Oh,
actually.
Y.
So this is Y, yeah, this is Y.
Oh, Y, yeah.
Yeah.
Set the G to Y as the capital Y.
Yeah, so okay, so we're gonna use capital Y here.
And M subscript B times big Y.
M subscript B times capital Y. Okay, so let's expand this out a little bit. If we say, so this is going to be something that looks like that. What is this? So here we have M times S. S is H times Y, which if we expand that, what is this really? G to the RY?
XY.
XY.
Oh, then.
Yeah. So if we want this
Yeah.
to look like this, what should we use here?
Z instead.
Yeah. Z. All right. Then our adversary is going to give back some B prime. And what does our machine B do with that answer?
Check with the private coin. It's same with my private coin.
All right, so we're going to check, does B prime match B, and if so, then we'll represent it here. So if B is equal to B prime, then what?
Output 1.
Yeah. So if output 1 and else we output 0. So if Z happens to be G to the XY, then this is a valid encryption. And if this is a valid encryption of one of them, what do we expect A to do?
Correct.
Yeah, it's going to give you B prime with some non-negligible probability. If Z is not, this is some random value, what do we expect from A?
1 to me.
Yeah, it's going to be 50-50. You have no idea what this actually is going to come out to. So based on that, we say machine B would break decision Diffie-Hellman if A breaks ElGamal. So by the principles of reduction, if this is actually hard, then ElGamal must be hard to break. And that's the principle of our reduction. So I've shown you a little bit more graphically here than sort of walking through step by step of the proof. But I hope that's fairly clear. Obviously, on exam you have to actually write this out a little bit more in words. But this is the core idea, is that you are constructing this machine. And there's a couple of gotchas here. The first is that this has to be polynomial time. If machine B is doing something where it's running A an exponential number of times, it's not going to work. It can run A multiple times. You could simulate run A a polynomial number of times, it's fine. But obviously not anything super polynomial. You then also have to show that this probability maps. I mean, even if you have some loss of probability, like, sometimes the response A gives you does not give you the perfect answer. So for example, here, if Z is actually random, if A happens to pick your B, then you're going to get the wrong answer. And you get the wrong answer less often than A is giving the correct answer. But that advantage is still non-negligible. And that's the important thing to show. So yeah, there's some formalities to this that I haven't covered, but this gives you the overall idea. If you look up the actual formal proofs, you can find formal proofs for ElGamal in many, many sources. Cool. Questions about this before we move on?
I think that for the DDH, the XY, they should be allowed to be equal to 1. Otherwise, if they choose the XY equals to 1.
I made these consistent just so that they fit. Theoretically, it doesn't actually matter.
Okay.
Because, I mean, theoretically, if you choose 0 or 1 here, then it's trivial, right?
What if X times Y equals to 1 over this?
If X
over P minus 1. It could happen a lot, possibly.
Okay, so I challenge you on that. It could happen a lot. I'll leave that as an exercise. If that were to happen, then yes, there are some things that you could do here. Yeah, if x times y happens to be 1 mod the size of your group, then yeah, you have a trivial attack here.
But this is a random sampling, right?
Yes, this is a randomly sampled
So
group.
happens long. Negligibly.
Yes, so my argument is that the probability of that happening is negligible, especially as Lambda gets big. Yeah.
I'd like to ask a question. So challenger is the challenger in the Diffie-Hellman. So for challenger and B, B
Yes.
is the adversary of the decision Diffie-Hellman, and challenger is the challenger of decision Diffie-Hellman. Is that correct?
Yes, exactly. So we're reducing from this problem to this problem. And so you have to start with the challenger for this. Yeah.
And B and A are playing a game of IND-CPA.
Exactly. So in between these two, it's this game. In between these two, it's that. Yeah. Yeah, that's the really critical thing to understand is how the direction of the reduction goes. It's really easy to get that confused.
Can I ask a logistic question? So it's going to be like a paper pencil type of quiz, or is it?
I honestly have not checked.
Oh, okay.
With Professor Vasadeva, I have not checked as yet. I would assume paper and pencil. I actually did a midterm in a different 5,000 level course last week, 2 weeks ago. I'm losing track of everything. Yeah, it was pencil and paper. But we were allowed to, for example, I do everything on my iPad. As long as I showed them that like my internet access was off, I could use it for all my notes and everything else. So yeah, I don't know whether I don't know any of the details on the exam yet. So I don't know if it's open book or not. Has Professor Vasadeva published anything on the, okay. Thursday. Ask Thursday.
I seem to remember a long time ago he said verbally that it is not an open book, but I don't know if he's changed his mind on that.
Yeah. Generally, we're not going to ask you to memorize things. Like, okay, I'm pretty certain Prabhat and I are on the same page. I would not expect you to memorize ElGamal. That's not the kind of course that we want to run. We don't want to be saying, memorize how this encryption works, how does RSA work, how does this work, and you just sort of rote memorize it. What we want you to be able to do is we'll give you some scheme. Maybe it'll be ElGamal, maybe it'll be like Schnorr signatures or something like that. And we'll ask you, like, here's an assumption, here is a scheme, prove this is secure, or give us an attack. That's what we want you to do. And that to me is you understand cryptography, you understand security. Memorizing these, they'll change sometime. RSA has been surprisingly long-lived. It's kind of shocking it's lasted as long as it has. And Diffie-Hellman key exchanges still are a thing, but that's largely because of elliptic curves. If we'd done them in just strict P-star, that would probably not be the case. But yeah. Okay, let's move on because
Sorry.
Yeah,
That's a very quick question. In case in case Z is really random, what's the best way to show that A can only win with at most a negligible advantage?
Sorry, which is really random?
In case it was really random, so GZ. Yes.
Z is random. basically what you're going to do is you're going to show here that this is at best a half.
Half plus negligible.
Yeah, and sorry, this case is yeah, this is a half plus negligible, and therefore what you end up with is in one case it's very high. So this probability is much higher than this probability.
Yes, now I get that. I mean, I was asking for that part where you show that in the random case it really is negligible. What's the best?
So this doesn't have to be negligible.
How-
This has to be more than negligible over this.
Right.
Yeah.
Okay, use it by assumption.
Yeah. Okay. I really want to get to this multiple ciphertext argument because this is again the hybrid argument. Quick show of hands, who here has looked through the hybrid argument for PRG stretch? 2 people. Okay, so roughly half-ish. Half plus negligible. Let's see. So this is going to be a similar flavor to that. And I don't think I need decision Diffie-Hellman anymore. Let this out, and hopefully you have it in your notes if you need to refer to it, but I don't think you will. And so this was on problem set 3, I think it was question 2. What happens if you have multiple ciphertexts? So now it's not just M0 and M1, now it's M0 as a vector, which is equal to M01, M02, etc. And you have M1 as a vector. 1, 1, 2. And these can be some t. I think technically that should be t lambda. And so t can vary with lambda. And then you get back here, you're going to get a C star vector, which is going to be encryption of CB1 under your public key, etc., etc. So this should be familiar to you. It was, again, on the problem set. I'm going to make a quick shorthand. So this is just a little sidebar. That I'm going to say CBI is always going to be the encryption. 1 lambda public key and I. So that's just going to make my word writing a lot easier to follow. Okay. I'm going to start with the case of just t is 2. It's going to be very similar to the PRG stretch. We'll talk about that for a little bit. If we get enough time, I will go through the general case. There's some gotchas in the general case. But if you can understand T2, you can understand the general case. So, what happens if T lambda is 2? So, we have some adversary. Given some adversary, I'll use blue line on here. Some adversary wins. This is just basic laws of probability. Given 0 plus 1/2 the probability that A wins if B happens to be 1. Which is the same as saying that. So I'm going to use this notation as a bit of a shorthand to say that we're using this adversary A, and I'm ignoring all of this setup and these other pieces. I'm just going to focus on what ciphertext we did. And so we're going to give it. Come on. I need to go through the short mode. Hang on, what's that aren't working? There we go. A vector like this. Rather than change the color. So this is all the same thing. This sort of boiled things down to this. So my question to you is, what happens if I do something funky like this? What does that mean? What's an adversary going to do? If you have some strong adversary here, what the heck is this? Because that's basically what we're going to do. I should have written this over here, but it's okay. You can use your imagination to imagine that these are side by each. So we're going to make another new machine B. Except B is going to play this game, while A is playing this game. So what am I reducing from and to here? I'm reducing from the single message to the multi-message. And what that shows is that if you can break multi-message, then you can break single message, and therefore multi-message is at least as hard as single message. Let's see. So, okay, so as in that game, we pick a random coin. We get our PK, our SK from keygen. We're going to send public key. We're going to send the public key on here. Here's where things start to get interesting. We're going to get this M0, M1, right? So, what should we do now? What can we do now? Can we send these as they are?
You need to pick, like, possibly there's at least one message in this vector that we can distinguish. You need to find out which. Right.
Or you could guess.
Could be. Or we just guess. Just pick one.
Yeah.
We're just going to pick one. So we're going to pick second, the last entry in each of these vectors. So remember that this is now going to just look like this. We only have two entries. This looks just like this. We're going to pick that and that. Send them on. So send those over. We're going to get back CB2. I'm just going to call that 2. And all right. So any thoughts? What do I need to send here? Can I send back just the one ciphertext?
You need to encrypt like all the others as well, and then back to the CB2.
Yeah. So immediately there's only 2. We're limiting ourselves to this case. So I could call this star, but just for clarity, I find this notation a little clearer. So I'm just going to arbitrarily pick. This is always going to be C0. Sets back some B prime, and we just forward that on. How does this make any sense? Let's break this down by cases. So, first the easy case. If b equals 0, what's the probability that we win? So winning here means that we have to produce b prime that is 0, given b is 0. So that means that we've gotten back C02. And again, remember I'm using this shorthand for all these encryptions. It just makes it quicker and easier and boring. What is this probability? What does this boil down to?
Probability that A wins multiple IND-CPA.
Yes. But in this case specifically, what did we give A?
C01, C02.
Exactly. So here, great. This is basically the form we're looking for, right? Looking at this. Hey, it's like we've gotten one piece of this. Hooray, we're a step closer. Okay, let's talk about a different case. So if b equals 1, what the heck did we get back here? What did we do to this adversary? So it was given, so b was given C12. Well, we want to know the probability that that's 1. And if we translate this into our A adversary, shortcut things, it's essentially identical. We just change this. Incorrect. Let's try it again. Right? So this is what we're trying to reason about. We're trying to say, what the heck is this? Well, let's talk about our overall probability. So from here, we can use a similar strategy. Say, this has to be 1/2 times the probability that b of basically, all I'm doing at this point is assembling all the facts that we know. I'm assembling, putting this and this into one statement about B. It's just a lot of algebra. Okay. Now, what do we know about the probability of B winning? Negligible. Specifically 1/2 was negligible, but that's the idea. We assumed this is secure. That we have single message security. So we know that this must be less than some negligible function. If you really want to add the lambdas in here, I'm going to drop them because we're running short of time. As always in this class. Okay, so we sort of found a bound. We say that, you know, this plus this weird thing is negligible. Okay, but we're still not to our goal yet. So, what happens if I change this? What happens if here, instead of doing this, I'm going to make a B prime, and this B prime is going to send, what am I sending? Yeah, I'm going to send, remember correctly, it's going to be 0, 1, and 1, 1, yes. Okay, and then here, so this is my prime, I'm going to send always whatever this is, and I'm going to send C1. So whereas before I always picked C0, here I'm picking C1. And what we're going to see is that this is sort of the complement. If you walk through all this algebra, what we're going to show is that the probability that this B prime wins is going to be 1/2 And you could call these negligible 1, negligible 2, and so on if you want it to be formally correct. I'm going to, again, sort of ignore that. So all that I've done is instead of taking the last one, I took the first one. And I said, throw those at my challenger and give to A what I get back. So that's why this one changes in the case that B is 0. I have 0 here. Case B is 1. I have 1 here. And then the last one, the second one, I always pick C1. And here's the overall idea. Similar to with the PRG stretch, where we hybridize. We said, you know, if you can distinguish between this polynomial number of bits that are truly random and are PRG, then you should be able to distinguish a single bit. This is sort of similar. We're saying if you can distinguish 2 messages that go from here to here, then you should be able to distinguish here and here. And if you can't distinguish here and here, and you can't distinguish here and here, then you can't distinguish between the 2 inputs. So if you can't distinguish these 2, you can't distinguish these 2, and you can't distinguish these 2. That's the idea. And if you show this mathematically, what we're going to do is we're going to sum these. So if, let's say this is equation 1 and this is equation 2, then 1 plus 2, we're just going to sum these vertically. I apologize for this getting a little bit low on the board. But notice that, just remove the halves for a moment. We basically have the probability of this, 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 and this. Well, hold on a second. The probability of A, C0, C1 equaling 1, then probably A, C0, C1 equaling 0. What can A output? Can A output anything other than 0 and 1? So what do these have to sum to? This has to sum to 1. Otherwise, you've got something very strange going on with the adversary. So you end up with 1/2 probability that A 0 plus 1 plus 1/2 and if we take this side, it's equal to 1 plus actually correction, this is it's a half times this plus this, so it's half. Okay. Well. Something I skipped here. A negligible function plus a negligible function gives you another negligible function. So technically this is negligible 1, negligible 2, negligible 3. They're not the same function, but you get the idea. I can take this out, and now this is 1/2. And ta-da, we have just shown that if the probability of B winning is 1/2 plus negligible, then the probability of A winning is 1/2 plus negligible. So it's sort of the reverse, like before we constructed something and said, well, the advantage of B is equal to the advantage of A times a factor. Here we sort of did the opposite. We said, if B is limited, then so is A. But you could rewrite this to use a similar argument. So that's the idea. Again, the intuitive explanation is if you have some adversary that can distinguish between the vector cases, then you can hybridize. You can say, well, you can't really distinguish this and this by the property of single message indistinguishability. And same thing here, you can't distinguish these two, and if you add these two, that has to still be negligible. So it's again this hybridization argument. So the general case sort of follows. Before we go to notes on the general case, I don't think we have enough time to go through all of it. Any questions on the two-message case?
Here you're trying to say that it is single IND-CPA secure, so it is multi-IND-CPA secure.
Yes.
Okay.
Yeah, exactly. Yeah. And we've done this by hybridizing, by producing a machine that does sort of one step of that. Okay. Any other questions before the general case? Okay, so the general case is the same thing, but more complicated. And make sure you understand this case, because then the general case will make a lot more sense. I'm going to define another shorthand, which is not really a function, but the idea is that wherever your T is. So the idea is, this is a vector of ciphertext where the first I entries are from the M zeros, and I plus 1 to T are from but one side. And so if we imagine for a second we have this, what we're also going to do now here, instead of just always picking one, we're going to have I is randomly sampled in 1 through t, and we're going to send back m0i and 1i, and here we're going to get back that. And what we construct here is going to look a little bit funky, but it's going to be, oh, come on. C0, 1, C0, and then I is that. Basically the same idea. So we're essentially out of time. Basically what happens is that if B is 0, then this looks like this. If B is 1, then this is just this C vector I plus 1. And you take cases. You go through and say the probability that B outputs 0 given B is 0, the probability that B outputs 1 given B is 1, and you sum all of those up. And just like here where you've had things cancel, not really cancel, but like probabilities have to sum to 1, you get a whole bunch of things that are going to sum to 1. And at the end of it, you've shown that the probability that A given the full vector of what it expects, plus have the probability that they get the full vector on the other side, has to be negligible times some polynomial factor. So here this was, I didn't write 2 because we don't really know what these negligible functions are, but if they happen to be the same, then this would be a factor of 2, right? If you have some polynomial number, then you're going to have some polynomial factor in your negligible functions. And that's the basic idea. I have a textbook reference for this. I'll post this on Canvas on the homepage. It's the same textbook that has the PRG stretch argument. As you can tell, that textbook does really well with hybrid arguments, so I do suggest reading it. The treatment of the textbook is more formal, obviously. You do have to step through it, but it presents you essentially this idea. If you can follow it for the case of 2, you can follow it for the rest of it. It's just more algebra. All there is to it. But it's the same idea. And again, it's the same idea as the stretch argument. Basically, if you can distinguish between this all being C sub zeros and this being all C sub zeros except for the last one, and then distinguish the 2 back, 3 back, 4 back, and then all the way through. At some point, there has to be something greater than negligible. And if that is greater than negligible, then your single message is greater than negligible, and therefore you've broken single message security. Questions? I'm through my notes to see if there's any gotchas that I missed. I sort of ran through this last part real quickly. Yeah. So yeah, this choosing of I makes the argument a little bit more complicated, but again, it just turns into algebra. It's basically the same as this B and B prime that we had up here before. If it makes it easier for you to think of them as separate machines, where you have, T lambda different machines, and then you sum all them up, you can do that too. Same idea works. Cool. think that's it. If you have any questions about anything for the midterm, please post them on Canvas. Do bring your questions about the logistics for the midterm to Thursday's lecture. And wish you all the best of luck. Again, use Canvas, and I'm glad to help you out any way I can to get through this midterm. Thank you.